Hello, everyone. Good evening.
Hello.
Hello. This is my first time to say good evening. Every time I say good morning. Okay. So today I'm going to go over the 3 chapters that will be covered in the exam. I will try my best to cover everything I remember. And then if you have any question, please let me know. So the exam will be 4 questions. Some of them will ask you about the concept. Some of them will ask you about what are these and definitions. Some definitions, but in terms of what you from your understanding, you don't need to memorize everything in details. And some of them will need some calculations. And I will not ask you to do anything by R. And I think the exam will not take more than 40 minutes. So you have 10 minutes to think about the questions. And also, I think about coming to the class early, a little bit, something like 10 minutes or more. So if you would like to start this exam early, because we have a class right after our class. So I will not be able to give you more time after the class, but I will send an announcement that I will come early. So if you came early, you can start this exam early. Something like for the first class, I have the class at 9:05. So I will come at something like 8:50 or 8:45. So you can come and start this exam early. For the second section, it is at 11:15. Maybe I will come at 11. So if you'd like to start at 11, you can do it. So, but because I will not be able to give you much time after the class, because we have there is a class after us directly. So I will send an announcement about this one. Okay, do you have any question? Any question before I go over the 3 chapters? Okay, so let me set up my computer because I will write on the screen. 1 second. Everyone can see the whiteboard? Whiteboard?
Yes.
Okay, great. So let me start chapter 1. See what we covered in chapter 1. Chapter 1. Oh, come on. Chapter 1. In chapter 1, we learned some statistical terms that is very famous in design. Like we learned what do you mean by why this one? We learned what do you mean by experimental units? What do you mean by observation units? We learned what do you mean by treatment factor? What do you mean by blocking factor? Treatment, placebo, control group. we learned what do you mean by these kind of things, like how many, if I asked you, how many experimental units, you think about what you are working with. Am I working with shrimp? So how many shrimp? If or you can think about as when I assign the treatments, to assign the treatments to what? If I assign the treatment to the students, so how many students I have? Assign the treatments to patients, how many patients I have? I assign the treatments to tanks, how many tanks I have, and so on. This is how to count how many experimental units. How many observation units? You think about the response variable, you measure. I measure the response variable from what? I measure the response variable from shrimp, so how many shrimp? I measure the response variable from students, so how many students? I measure animals, so how many animals I have? I measure the plants, how many plants I have? So when you think about the observation units, you think about the response variable that you measure. And when you think about the experimental units, you think about the treatments you assign. You assign them to how many? The treatment factor is the factor you are interested in. That factor has some levels, and each level is a treatment. Unless you have many treatment factors, if you have many treatment factors, the number of combinations is the number of treatments. But if I have a treatment factor, only one treatment factor, the levels of these factors are the treatments. The blocking factor is another factor, but I'm not interested in this factor. I know as a researcher, it may affect my results. It may affect my response variable, but I'm not interested in that factor. So I include it as a blocking factor. So the treatment factor is the variable you are interested in. The blocking factor is a confounding variable that you are not interested in, but you include it in your study as a blocking factor to control its effect on the response variable. The treatment can be the level of the treatment factor you are interested in, or can be a combination of the levels of the treatment factors you have. So if you have one treatment factor, the number of treatments is the number of levels of these treatment factors. But if you have two treatment factors, one of them has 2 levels and one has 3 levels, so the number of combinations, or the 2 times 3 is 6 treatments. So number of treatments is the number of combinations if you have more than treatment factor. The placebo is one of the treatments, but is a fake treatment. Or sometimes is not a fake treatment, sometimes is the old one. For example, if we have an old drug, it is very famous and it's used for long time, and now we have 2 new drugs. We consider these 2 new drugs are 2 treatments and the old one as a placebo, or something I need to control to compare the other treatments to this old one. So the placebo in medicine, actually, this one is always a fake thing, fake treatment. And the people who receive the placebo is called the control group. So I call them control group because I want to compare the other groups to this group. So in chapter 1, we learned the meaning of these kind of things. And also we learned something called fundamental principles. Fundamental principles. These fundamental principles, they are some elements or some factors. They are associated with design. It's not in the observational study. It is something related to design, like randomization, replication, blocking, and we added one more is not in the lecture note, but we added one more, is called blind or double blind. Blind or double blind experiment. So assuming I have a treatment factor is temperature. Assuming I have a treatment factor is temperature. And I selected 3 levels, temperature 1, temperature 2, temperature 3. So I have 3 treatments because I have only one treatment factor, which is temperature, and it has 3 levels. So these 3 levels are 3 treatments. Randomization mean, let's start by replication. Replication mean I should assign more than one experimental unit to each treatment. If I assign only one treatment, if I assign only one experimental unit to each treatment, I will not be able to estimate sigma square. So I need to have more than one experimental unit assigned to each treatment, at least 2. At least 2. I can have more. So this is replication. It means I repeat the whole experiment more than one time. So in this case, I repeated the experiment 4 times. So 4 replication. Randomization means when I assign these experimental units to the 3 treatments, or the 3 treatments to the experimental unit should be randomly assigned. So I randomly assign the experimental units to the treatments, or the treatment to the experimental units should be randomly assigned. So we need to avoid bias. The third one is blocking. Sometimes the blocking factor is a confounding variable. I included in my study as a blocking factor. For example, gender. Maybe gender affect my response. Maybe immune system affect my response. Maybe education level affect my response. So each education level is a block, or each gender is a block. So within each block, we are going to assign randomly all the treatments. So in the blocking, I have blocks, and within each block, I should randomly assign all the treatments like T1, T2, T3, like in chapter 4, but in chapter 4 will not be covered in the exam. But we should be familiar with the idea of blocking only for exam 1. The fourth one, which is the last one, is blind and double blind. The experiment should be blind if I can make it as a blind, because sometimes I will not be able to hide the treatments from the participants, because the participant, I have to show the treatment to the participants, but sometimes I can hide the treatments, or I can make all the treatments similar to each other. So the participants will not be able to tell which treatment he received or she received. This is blind. Double blind means the researcher, the participant doesn't know which treatment they received, and also the researcher doesn't know which one received which treatment. So who knows? Someone else will do the assignment, they randomly assign. So sometimes this experiment is blind, sometimes double blind. If you can make it blind, it's fine, you can do it. If you can make it double blind, it's fine, but sometimes we will not be able to do blind or double blind. So randomization, you have to have randomization. Replication, you have to have replication. But blocking and blind and double blind, these if you can do it. If you have some confounding variable included as a blocking factor. But sometimes there is no confounding variable, so it's fine. For the blind and double blind, sometimes I'm able to make all the treatments similar, but sometimes you will not be able to do it. So these two, if you are able to do them, it's fine. If you are not able, it's fine. But these two, randomization and replication, you have to have these ones in your experiment. So it will be a good experiment. Guys, if you have any question at any time, unmute yourself and ask the question. You don't wait. Any questions so far?
Could you go over the difference between experimental units and observational units one more time?
Okay, experimental units and observation units. When I say how many experimental units, think about the treatments. Keep in your mind the placebo is also a treatment. So think about those treatments. When you assign them to what and how many? I assign them to the students. So how many students is the number of number of students is the number of experimental units. I assign them to the dorms. So the number of dorms is the experimental units. I assign them to tanks. So a number of tanks is the number of experimental units. I assign them to patients. The number of patients is the number of experimental units. But the observation units, when I ask, what is the number of observation units? You think about the response variable. When I measure the response variable, I measure the response variable from what? I measure the response variable from the plants. So how many plants you have? I measure the tank, I measure the patients, how many patients you have. I measure the students, how many students you have. So when you think about the experimental unit, think about when you assign the treatments, you assign them to what and how many. But when you think about the observation units, you think about the response variable when you measure. I measure the response variable from what and how many. Does it answer your question?
Yeah, thank you.
You're welcome. Any other questions?
Yeah, so if you assign a treatment directly to the students without placing them in dorms or any other container type thing, then experimental and observational unit would be the same value?
Very good. Like in the homework. In the homework when we assign the soups to the dorms, we didn't put the soup in each student room. We put the soups in the restroom of the dorm. So when I assign the soups, I assign them to the dorms. How many dorms? They were 20. So number of experimental units is 20 because each dorm is an experimental unit. But when I measured, I did measure the response, which is the number of visits. I didn't measure the dorm. I measured the students. So I asked every student how many visits. So I measured the students. How many students? They were something like 2,400. So number of observation units is 2,400. But number of experimental units was 20 dorms.
Okay, got it. But then if it was assigned directly to the student, then it would be 2,400 as well.
Very good.
Okay.
So the number of experimental units equals the number of observation units in this case.
Okay, thank you.
Yeah, welcome. Any other questions?
Yes, I posted in chat. I asked the difference between treatments and treatment factors and how you can tell how many of each are in a study or experiment.
Yes. Okay, the difference between treatment and treatment factor. Like if I set temperature, this is the treatment factor. But the levels of this temperature are the treatments. So if I have only one treatment factor, this one is called the treatment factor. And those are the levels, those are the treatments. So in this case, I have one treatment factor, 3 treatments.
Okay, gotcha. So if I were to say that, like, I created an experiment where we determine whether temperature can affect the plant's growth, would you say that temperature would be your treatment factor and that the varying levels of temperature would be your treatments?
Yeah, so the temperature is the treatment factor and the three levels are the 3 treatments.
Okay, gotcha.
Any other questions? Okay, so let's go to chapter 2. Let's go to chapter 2. 1 second, because I see someone near. Please mute, unmute. Okay, now it's fine. So let's go to chapter 2. Chapter 2 is simple comparative experiment or design. Simple comparative design. In this chapter, we covered 2 cases two independent samples and two dependent samples. The two independent samples generalized in chapter 3, two dependent samples generalized in chapter 4, which is not included in the exam. So in the two independent samples, looks like we have one treatment factor, and that treatment factor has two levels. So we have two treatments we need to compare. These two treatments may be a treatment and a placebo, or two true treatments. So for the two independent samples, we covered the assumptions. And for the dependent samples also, we covered assumptions. The assumption for the two independent samples are, the first one, the two samples are independent. The second one is the two samples are randomly selected. The third one is each sample is randomly selected from normal. But for the dependent samples, the assumptions are the two samples are independent. What do you mean by the two samples are dependent? I mean, I measured one sample two times, like before and after. The second assumption is normality. But normality not for each sample, normality for the difference. For the differences between the two samples. Because in this case, I have one sample measured twice, before and after, before and after. So we have two groups of data. And then we calculate the difference, first one minus this, second one minus, 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 and you get differences. These differences should follow normal distribution. So how do I check normality? You check normality by looking at the QQ blot or Shapiro test. But the random samples, like independence, you don't need to check this assumption. From design itself, you can tell if they are independent or dependent. And the two samples are randomly selected from the scenario itself. You don't need to check this one. But the only thing you need to check, each sample is randomly selected from normal. It means each data follows normal distribution. You can look at the QQ blot, or you can look at Shapiro test. For the other case, dependent, from the scenario itself, you read the question, looks like dependent or not. Normality, you need to graph the QQ blot for the difference between the two groups of data. And you look at the Shapiro test for the difference between the two groups of data. For the independent case, we covered also the statistical model. Also for the dependent case, we cover the statistical model. We need to be familiar with the statistical model. The statistical model for the independent samples is Yij equal mu plus tau I plus epsilon ij. And I equal 1 and 2, j equal 1, 2, up to little n. For the dependent case is Yij equal mu plus tau I plus beta j plus epsilon ij. and I equal 1 and 2, j equal 1, 2 up to n. The difference is what? I added the effect of the individual because I measured every person 2 times. So I need to estimate the effect of the individuals that I measured. And I is the same 1 and 2, j is the same 1, 2 up to n. You can add these assumptions in only one statement like epsilon ij follows normal with mean 0 and sigma square. So normality with mean 0 and the constant variance sigma square. Or you can make it a sigma I square. It depends on what? And I equal 1 and 2. It depends on the other assumption, one more assumption, which is equal variances. Because in this case, we cover 2 cases. We cover for the independent samples, we covered sigma 1 square equals sigma 2 square, and sigma 1 square doesn't equal sigma 2 square. This assumption is very important in terms of what? The formulas, because we cover the formula for confidence interval and we cover a formula for test of hypothesis. This assumption affects the formula. But the dependent case, we do not cover sigma 1 square equals sigma 2 square because we do not work with 2 groups. We work with only one group of differences. Any questions so far? Any questions so far? Yes.
So you mentioned that in the independent samples, we don't have to do the Shapiro test to test for normality. Is that right?
For the independent case,
Yes.
you test, this one is normal distribution, you test using Shapiro test.
So we do the Shapiro test for the independent case as well, right?
For the independent, but dependent, we do, but the difference is what? In 2 independent samples, we do the test 2 times. 1 time for the first group, 1 time for the second group. But for the dependent case, we do it only 1 time for the differences.
Okay, it makes sense. Thank you.
Yeah, welcome. Any other questions? Okay, so let me cover the formula for sigma 1 square equals sigma 2 square, and sigma 1 square doesn't equal sigma 2 square. So 2 independent samples. We covered confidence interval and testing. Confidence interval, the formula is, 2 independents, the 2 cases. The 2 samples, we have 2 cases. Sigma 1 square equals sigma 2 square. Sigma 1 square doesn't equal sigma 2 square. For the confidence interval, the formula for sigma 1 square equals sigma 2 square is y1 dot bar minus y2 dot bar plus or minus t at alpha over 2 and degree of freedom. This one from the t distribution table, it should be given in the exam, times sp times the square root of 1 divided by n1 plus 1 divided by n2. So the degree of freedom in this case is n1 plus n2 minus 2. And sp equal square root n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2. This is the confidence interval for the difference when I assume sigma 1 squared equals sigma 2 squared. But if I assume sigma 1 squared doesn't equal sigma 2 squared, the confidence interval is y1 dot bar minus y2 dot bar plus or minus t at alpha over 2 and degree of freedom times square root 1 divided by, say, s1 squared divided by n1 plus s2 squared divided by n2. So what is the degree of freedom in this case? The degree of freedom, if you assume sigma 1 squared doesn't equal sigma 2 squared, is not n1 plus n2 minus 2. It is a very big formula. S1 squared divided by N1 plus S2 squared divided by N2 all square divided by 1 divided by N1 minus 1 times S1 squared divided by N1 all square plus 1 divided by N2 minus 1 S2 squared divided by N2 all square. This is the degree of freedom if you assume sigma 1 squared doesn't equal sigma 2 squared. So how do I know that sigma 1 square equals sigma 2 square or sigma 1 square doesn't equal sigma 2 square? How do I test this assumption? Test or check the assumption. Check. How do I check the assumption? Because I would like to know which one I should use, which formula. There are two ways. The rule of thumb said S maximum divided by S minimum. If the S maximum divided by S minimum, this ratio is less than 2, assume sigma 1 square equals sigma 2 square. If it's greater than 2, assume sigma 1 square doesn't equal sigma 2 square. Or there is something better than this one. You do the F test for equal variances. And we use the R for this test of equal variances. If p-value, I assume the equal variances if the p-value greater than 5% of this test. But in this case, I will give you the output of R and you look at the p-value and you decide sigma 1 square doesn't equal sigma 2 square or sigma 1 square equals sigma 2 square. If p-value is greater than 5%, you assume sigma 1 square equals sigma 2 square. If p-value less than 5%, you assume sigma 1 square doesn't equal sigma 2 square. So this is confidence interval. What about test of hypothesis? Test of hypothesis. Sigma 1 square equals sigma 2 square. Sigma 1 square doesn't equal sigma 2 square. For testing, H0 is the same. H0, mu1 equal mu2. H1, mu1 doesn't equal mu2. The same thing for the other one. H0, mu1 equal mu2. Against mu1 doesn't equal mu2. The second step is the same. Alpha, alpha. The third step, they are different. T0 equal, T0 equal. If you assume sigma 1 square equals sigma 2 square, it will be y1 dot bar minus y2 dot bar divided by sp times square root of 1 divided by n1 plus 1 divided by n2. But if you assume unequal variances, it is y1 dot bar minus y2 dot bar divided by square root s1 square divided by n1 plus s2 square divided by n2. And this is the first step, second step, third step. The fourth step is the same p-value. The step number 5 is the same p-value. So how do I get the p-value? Using the applet. I will give you a screenshot from the applet so you can find the p-value and then you take your decision. They are the same. So they are different in the step number 3 because if I assume equal variances, I will use SP. But if I assume unequal variances, I will work with S1 and S2. This is the two independent samples. What about the dependent samples? The assumption of the independent samples. We talked about this one. The statistical model of the dependent samples. We already talked about this one. So we talked about this one. But we didn't cover the confidence interval for the dependent samples, but we cover the test of hypothesis. So let me write down the test of hypothesis for the dependent sample.
Professor, I have a question for.
Yeah, sure. Go ahead.
Yeah. So I got confused when we should use like equation to get the t-value and when we should t-table.
You p-value and the t-distribution table?
Yeah, sometimes like for confidence interval, we get it from table, and when
Okay,
we use the test.
know the confusion you have.
Yeah.
If you work with confidence interval, you get the t-value from the table. But if you work with test of hypothesis, H0 and H1, you get the p-value using the applet. So for the confidence interval, you need the t-value, which is at alpha over 2 and degree of freedom. You get this one from the table. But for testing H0 against H1, you need p-value from the applet. So the first one, confidence interval, I will print out the table itself. For testing, I will give you a screenshot from the applet. Does it answer your question or still confused?
So my question is it the same t value or different meaning?
The
Like
same
the one
p-value, you said?
Yeah, I mean like same meaning for both.
For the t and p-value?
No, for t value from the table and t value from equation. Is it the same meaning for the t or different meaning?
For the equation and the table, you mean?
Yes.
I think you mean T versus T0, right?
Yes, exactly.
Okay, good. Thank you. You mean t and t0.
Yeah.
The t from the table for the confidence interval and t0 that use this one to find the p-value, they are different.
Okay.
This one is called the critical value from the table, but this one is the test statistic value for test of hypothesis. So this one is called the critical value that I need for the confidence interval, and it is completely different from the T0, which is the test statistic.
Okay, this was my
That I
question. Thank
use
you.
to find the p-value. You're welcome.
Okay, thank you so much.
Any other questions? Okay, so let me cover testing for the dependent case. For the dependent case, the test of hypothesis, the first step, H0, mu of the difference is 0. It means the two treatments are the same, before and after is the same, because on average, the difference is 0. Against H1, mu d may be greater than 0, maybe less than 0, maybe it doesn't equal 0. It depends on the question, the research hypothesis you have. The second step is alpha, should be given. The third step, you calculate T0, which is x bar d minus mu d, which is always 0, divided by s d divided by square root of n. This is step number 1, step number 2, step number 3, step number 4. You find p-value using the applet. And the last step, you take a decision based on comparing the p-value to alpha. Step number 4 to step number 2. So this is test of hypothesis for the dependent case, but we didn't cover the confidence interval for the dependent samples. But for the independent, we covered the confidence interval and test of hypothesis. For the dependent samples, we cover the test of hypothesis, but we didn't cover the confidence interval. But if you'd like to have it, it's fine. It's very simple. X bar d plus or minus t at alpha over 2 and degree of freedom times sd divided by square root of n. This is the confidence interval for the difference between the two samples, the two population means of the two treatments. So, any question about chapter 2 so far? Any question about chapter 2? So again, I will not ask you to do anything by R during the exam, but maybe I will give you some output and ask you about the output. Any question?
Can you tell the difference between X? What's X bar D referring to?
Okay, let's go back to this one. I said we have two groups of data, before and after. We measured the same individuals or the same subjects 2 times, like before and after. Or we gave 2 treatments and we measured after the first treatment, the second treatment. We do not work with these 2 groups of data as independent samples. We work with the difference. So we have some values for the difference. If you calculate the average of these differences, it will give me x bar d. X bar d is the sum of the differences divided by n. So x bar d is the average of the differences you calculated. And what about SD? SD is the standard deviation of the differences you calculated. So I need to calculate the average of these values as the standard deviation of these values. So what is the standard deviation formula? SD is the square root of 1 divided by n minus 1 times the sum of d squared minus sum of d all squared divided by n. But in the exam, I will not ask you to calculate these kind of things because it takes much time. But the homework is fine. I can ask you to calculate SD and X bar D and these kind of things. Any other questions? Okay, so let's go to chapter 3. Chapter 3. This one is the generalization of two independent samples because we covered two independent samples and two dependent samples. This one will be generalized in chapter 3, and this one will be generalized in chapter 4. So in this case, we have only two treatments, but now I will have more than two treatments. In this case, in chapter 2, my treatment factor has only 2 levels, but in chapter 3, my treatment factor has many levels. So we have many treatments. So let's generalize the two samples. In chapter 3, which is complete randomized design. In complete randomized design, we have one treatment factor, but it has many levels like treatment 1, treatment 2, treatment 3, treatment 4. And for each treatment, we assign some experimental units. We assign some experimental units. So we have replication and we assign them randomly. So we have randomization and so on, but we do not have a blocking factor so far. So what is the statistical model for the complete randomized design? The statistical model, like in chapter 2, it is Yij equal mu plus tau I plus epsilon ij. Where is the generalization? In chapter 2, I is 1 and 2, but in chapter 3, 1, 2, 3 up to A. And J is 1, 2 up to N. So we generalize this one. It is not 1, 2, it is 1 to A because we have many levels. In general, A levels for our treatment factor. So what about the assumptions for the one-way ANOVA or the complete randomized design? The assumptions are 3 assumptions: normality, constant variance, and the last one is independence. So I can write all these 3 assumptions in only one assumption, like epsilon ij follows normal distribution with mean 0 and the standard and variance sigma square. So sigma square doesn't depend on R. And sometimes you write it down as IID, independent, identically distributed normal with mean 0 and sigma square. So independent, one of the assumptions, identically normal, second assumption, with sigma square, not sigma square I or sigma I square, so it constant variance. How do I test these 3 assumptions? You can look at the graph or you can do test of hypothesis. So for normality, I look at the fitted versus residual graph, or I do Shapiro test. For constant variance, for the constant variance, you look at the fitted versus residuals. Let me for the constant variance, you look at the fitted versus residual, but normality, you look at the QQ plot. QQ plot. I should have the dots making a straight line. But for the constant variance, you can look at the graph, which is fitted versus residuals. I should have something like this one, randomly scattered above and below zero. Or you can run Levene test. And I need p-value to be big. For independence, I look at the graph, which is the residual order against residuals. I shouldn't see any pattern. I see the values above, randomly scattered above and below zero. Or I can look at the Durbin-Watson test. For tests, I need all the p-values to be greater than 5%. For Shapiro test, I need p-value to be greater than 5% to fail to reject H0 that says normality is satisfied. For Levene test, I need p-value to be big to fail to reject H0 that says P1 sigma 1 square equals sigma 2 square equals sigma C3 square up to sigma A square. For Durbin-Watson, I need p-value to be big to fail to reject H0 that says independent. This is how I check the three assumptions, and this is the statistical model and the layout of the design. And then we talked about the idea of fixed and random effect. This model, Yij equal mu plus tau I plus epsilon ij. Sometimes we work with the treatments as a random sample from all the possible treatments. So this one can be a random effect, can be fixed effect. Whatever you work with random effect or fixed effect for the treatment factor, the ANOVA table is the same. The way you calculate the values, the numbers in the ANOVA table is the same. But the difference is what? The difference is the meaning of these numbers, and the p-values are used to test what? If we have a fixed effect, the p-value is used to test, p-value is used to test H0, mu1 equal mu2 equal up to mu A against at least one is different. But the p-value, if I assume random effect, the p-value is used to test H0, sigma tau square is 0, or sigma tau square is not 0. You see, the way you calculate the values in the ANOVA table is the same. You do not change anything. But the p-value in your table is used to test mu1 equal mu2 up to mu A, or at least one is different if you assume fixed effect. But if you assume random effect for the treatment factor, the treatment factor is random, you use p-value to test H0, sigma tau square equals 0 against sigma tau doesn't equal 0. But the way you calculate the values in the ANOVA table is the same. So let's work with the fixed effect first. Any questions so far?
Yeah, Professor, for this. Oh, sorry. Go ahead.
Okay, so what is sigma referring to here?
Okay, sigma tau square refer to what? The variability due to the treatment factor. Because, for example, when we work with the temperature, maybe you look at these levels of temperature as a random sample from all the possible temperatures. I'm not interested in these specific 3 temperatures. I selected those as 3 levels of the temperature. Does the temperature levels are different in terms of the response variable or not? So if sigma square is 0, it means there is no effect of the temperature on the response variable. It means the levels of the temperature are not different in terms of the response variable. So if I failed to reject sigma tau square equals 0, it means there is no effect of temperature on the response variable because there is no variability due to the treatment factor. On average, the response variable on average is the same for all the possible levels of temperature. So sigma tau square is the variability due to treatment factor in general. If the variability is 0, it means on average, the response variable is the same, whatever the level of the temperature. Does it answer your question?
Yes, thank you.
You're welcome. Any other questions?
Yeah, Professor, to check the assumption, normality, and constant variance or independence, should we always compare with 0.05 or it depends on like the confidence interval given in the question?
It does not depend on the confidence interval. It depends on the researcher himself. What is the significance level you would like to use in your study? And keep in your mind, there is something we covered by the end of chapter 3, which is power analysis. You already selected the significance level that you compare to the p-value from the very beginning. You already selected significance level to determine the sample size. That one should be used by the end of the analysis. And you compare it to the p-value. See my point?
Yeah, so the one we are going to use in our test, we use it to check our assumption as well, right?
Yeah.
Thanks.
Yeah, welcome. But I got your question. You mean the assumptions and the testing?
Yes.
For assumptions, some people use 5%, some people use 10%. The people are very conservative, use 10%. The people are not that much conservative, they use 5%. This one is independent from the significance levels that you used to determine the sample size. Sorry for the confusion.
Thank you.
So for the, you're welcome. For the assumptions, some people use 5%, some people use 10%. But for the test of hypothesis, mu1 equal mu2 equal mu3, this one, the significance level is the one you used in the very beginning to determine the sample size in the power analysis. Any other question? Okay, so then we talked about what if we rejected H0? If we rejected H0, it means at least two are different. So to find which ones are different, there are many ways to find which ones are different using the multiple comparisons methods. We cover 4 methods. And we said that you shouldn't use t-test to compare H2 treatments. Because in the lecture note, I calculated the overall significance level. If we use the t-test to test mu1 equal mu2 or not, mu1 equal mu3 or not, mu1 equal mu4 or not, and so on, the overall alpha get inflated. And we calculated this one in the lecture note, and we found the significant, if we use 5% to each test, the overall significance level will not be 5%, it will be greater than 5%. So there are some methods or some people, they recommended some solution to this problem. The first guy, his name is Panfroni. This guy said to test H0 again, which says mu I equal mu J against mu I doesn't equal mu J and I doesn't equal J, you should compare the Yij, or sorry, Yi dot bar minus Yj dot bar. Compare the absolute value of this difference to this value, which is T alpha over 2 and degree freedom big A minus 1, big A minus A. You can write it down as big N minus A, or A times little n minus 1, or the degree freedom of error from the ANOVA table times the square root of MSE times the square root of 1 over Ni plus 1 over Nj if they are different. If the absolute difference is greater than, you reject H0. Reject H0. Otherwise, you fail to reject H0 and declare that the two averages are the same. So where is the modification? How he
That's
how
what I
he
need
solved the
fun.
problem? He
Fine.
divide.
Yeah, but
Go
like,
ahead.
we're funny.
Hello. He divided alpha by 2c. This is a contribution of Panfroni. He doesn't use alpha over 2, he used alpha divided by 2c. What is c? Is the number of pairwise pairs you are interested in. So if you have 4 treatments, so your number of pairs is 4, choose 2 is 6. So C should be 6, but sometimes we are not interested in comparing all the treatments. Maybe we are interested in testing only mu1 and mu2, mu1 and mu3. So only two pairs. So C will be 2. So sometimes C is not the maximum number of pairs. So it can be less. So this is the contribution of Panfroni. He suggests to divide alpha by 2c, not 2. And the confidence interval is what? Based on Panfroni. The confidence interval is you only change greater than to be plus or minus. So it will be yi dot bar minus y j dot bar plus or minus t at alpha over 2c big N minus A square root of MSE times the square root of 1 divided by Ni plus 1 divided by Nj. This is the confidence interval for what? Confidence interval of for mu I minus mu j at some significance level. This is the contribution of Panfroni. Tukey said, the second guy is Tukey. Tukey said, I'm not going to use T value. I'm not going to use this critical value. I'm not going to use the T distribution table. I'm going to use my Owen table. So I will compare the absolute value of yi dot bar minus yj dot bar to this value, Q alpha A F times the square root of MSE divided by N. So what is A? This is the number of treatments. What is F? Is the degree of freedom for error, which is big N minus A. So he said, if this absolute value is greater than this value, you reject H0. What about the confidence interval? You change greater than to be plus or minus. It would be yi dot bar minus yj dot bar plus or minus u alpha at A and F times the square root of MSE divided by N. So how do I find these values? U alpha. You go to the Tukey table. There are 2 tables for Tukey, one at 5% and one at 1%. Use the one which is matches the significance level. And the first row, find A. What is A? The number of treatments. Find A, first row. And find F, first column. The intersection is this value, the Q value. And MSE from the ANOVA table, little n from the number of replicants. This is the contribution of Tukey. And then there is another one, his name is Dunnett. This guy came and said, I'm not going to use the Tukey table. I'm not going to use the modification of Panfroni. I'll use my Owen table and I will compare yi dot bar minus yj dot bar to d at alpha and a minus 1 and f minus 1. F is the degree of freedom again of the degree of freedom of error, which is big N minus A. And A is the number of treatments, so number of treatments minus 1. So you go to the table, there are two tables, one for 5% and one for 1%. And you select the one, match the significance level, and find A minus 1 first row and F first column. The intersection is this value. Multiply this value by the square root of MSE times 1 over Ni plus 1 over Nj. If they are equal, Ni equal Nj, this one will be the square root of 2 MSE divided by little n. If they are equal, if Ni equal Nj, if it is balanced design. And he said, if this absolute value is greater than, reject H0. Otherwise, fail to reject H0. What is H0? Mu j, mu I equal mu j. And the confidence interval, you change this one to be plus or minus again. So it will be absolute, it will be yi dot bar minus yj dot bar plus or minus d alpha at a minus 1 and f times the square root of MSE times 1 over Ni plus 1 over Nj. The last one is Fisher, and keep in your mind, oh, 1 second. This one is, what is the name of this guy?
Done.
This is Dunnett. Oh, so if it is Dunnett, I need to change J to be A, because Dunnett, this one should be used if I have a control group. If I have a control group. So I need to change J to be A, assuming A is the control group. Assuming J is the control group. So I need to change Y, it will be yi dot bar minus ya dot bar. Assuming A, the last one is the control. And I need to change what else? 1 divided by Ni plus 1 divided by Na. If Ni and Na are the same, so this part will be square root of 2 MSE divided by N. Because in Dunnett is used when I compare all the treatments to a control. So I need to change J to be A. Assuming A is the control group. The last one is Fisher. Fisher said, I'm not going to modify anything. I'm going to use T distribution as, but alpha will get inflated. He said, okay, no problem. I don't care. But you shouldn't use it unless the design is balanced design. Fisher or balanced design. You shouldn't use it for the unbalanced design. And he said, I will compare the yi dot bar minus yj dot bar to the t value at alpha over 2 with no modification. Is not alpha divided by tc. And big N minus A, or the degree of freedom for error from the ANOVA table, times the square root of 2 MSE divided by N. If this absolute value greater than this value, reject H0. Otherwise, fail to reject H0. And the simultaneous confidence interval will be yi dot bar minus yj dot bar plus or minus t alpha over 2 and big N minus A times the square root of 2 MSE divided by N. So the simultaneous confidence interval is, you don't need to memorize both the testing and confidence interval, because in the simultaneous confidence interval, just to change greater than to be doesn't equal plus or minus. You change this one to be plus or minus. So you don't need to memorize two formulas, although you will write these kind of formulas in your formula sheet. But testing and confidence interval are similar, except you change the greater than to be plus or minus, and you remove the absolute value. Those are the 4 methods ordered based on which one is the most conservative and which one is the not conservative. Any questions so far?
Yeah, Professor, for Dunnet, we have 4 tables, 2 for one-sided and 2 for two-sided. Which 2 tables should we use?
You should use the 2 tables for the two-sided, because C, the alternative is doesn't equal. So the alternative doesn't equal, it means two-sided. But for some reason, maybe the researcher is interested in greater than or less than. In this case, you should use one-sided. But in our case, we compare the treatments and they are equal or not equal, equal or not equal. So in this case, I have equal, against doesn't equal. So my test of hypothesis is two-sided. So you use the 2 tables of the two-sided.
Okay, thanks.
Any
I have-
other question? Yeah, sure.
Yeah, I have
Go ahead.
another question. So for the R result, if we have Bonferroni or Tukey, should we compare like this individual pairs using the alpha individual or alpha overall? I mean,
Alpha overall. Very good question. Because these confidence interval are called simultaneous confidence interval. So when I estimate the confidence interval, I estimate them at the same time simultaneously. When I do the tests, I test all of them simultaneously at the same time. So I should compare the adjusted p-values to the overall significance level, is not the individual significance level. So we compare the adjusted value to 5%, because in our code, all of them, the overall significance level is 5%.
thank you so much.
You are welcome. Any other questions? Okay, then we covered the contrast. How do I know the contrast is? The contrast in general is what? Is a linear combination of the population means or the treatment means. So in general, C is sum of CI mu I. So this one is C1 mu1 plus C2 mu2 plus up to the last one, CA mu A. This is a linear combination of the treatment means. So how do I make a confidence interval for this one? Because it is a function of unknown values. Mu's are unknown. And how do I do test of hypothesis? The confidence, before you do test of hypothesis or the confidence interval, you need to make sure the sum of CI is 0. If the sum of CI is 0, this contrast can be estimated, can be tested. But if the sum of CIs, the sum of these guys is not 0, it is not a contrast. You shouldn't estimate this one. You shouldn't do a test or confidence, do testing or confidence interval. So the confidence interval for the contrast is C hat plus or minus T at alpha over 2 and degree of freedom times the square root of MSE divided by n times the sum of CI squared. This degree of freedom is degree of freedom of error big N minus A, or A times little n minus 1, or the degree of freedom from the degree of freedom for error from the ANOVA table. So how do I estimate C hat? The estimation of C hat is the sum of CI mu I hat, which is C1 times Y1 dot bar plus C2 Y2 dot bar plus up to the last one, CA times YA dot bar. This is the estimation for the contrast. And then you plug in this one in the C hat and you find the T value from the table and the MSE from the ANOVA table, little n, and then you calculate sum of CI squared. This one is square plus this one is square up to plus this one is square. You give me the sum of CI squared. You plug in the values in the formula and you get lower limit and upper limit. If you'd like to do testing, for testing, the first step, H0, the contrast is 0. H1, the contrast is not 0 or greater than 0 or less than 0 based on what you are interested in. The second step is alpha, should be given. The third step, you calculate T0, which is C hat, the one you calculated, this one, minus C, which is 0 because in the null hypothesis is C equals 0, it's always 0, divided by square root of MSE divided by N times the sum of CI square. You already calculated this one. You get the value of the T0, use T0 in step number 4 to find the p-value using the applet. The last step, a decision. Done. This is the testing for the contrast and the confidence interval for contrast. Any question? Any question?
Could you go over the CI squared and how to calculate that?
CI squared, this one?
Yeah.
Okay. So let me give you an example to explain the CI squared. Maybe like in the homework. In the homework, H0 says, test this one. The average of the control equals the average of treatment 1 and treatment 2. So this is the contrast we need to estimate and do confidence interval. So before you need to find what is C1, C2, and C3. This one can be written as mu control minus half mu treatment 1 minus half mu treatment 2 equals 0. So C1 is the value next to the first one. So C1 is 1. C2 is negative half. C3 is negative half. So the sum of CI square is 1 square plus negative half square plus negative half square. It is 1.5. This is how to find the sum of CI square. Got it?
I have a question. How to calculate for the p-value or how to find it?
Could you please repeat your question? I couldn't hear you.
The question we have on the slide, lecture slide. How do we get the
This one?
yeah, this one.
Okay, what is your question?
How to get the p-value?
You know how to get this t value?
Number 4, the p-value.
Number 4, the p value is this one?
Yeah.
This one using the applet. But in the exam, I will give you a screenshot from the applet because you are, I will not ask you to calculate this one during the exam from the online applet. I will give you a screenshot from the applet, so it will be given.
Okay, thank you.
But if you'd like to calculate it for the homework, you need to have 3 numbers first. You need to know what is T0 before you go to the applet. What is the degree of freedom before you go to the applet? And the alternative is greater than or less than or doesn't equal. You plug in these 3 information in the applet, it gives you the p-value.
So in the homework, I should calculate this one.
In the homework, you should be able to find this value using the applet.
So they tell me directly, right?
Well, I didn't get your question, sorry.
So in the homework, they give me the p-value directly, right?
In the homework, it doesn't give you the t value. That you need to calculate this one, the T0. You need to calculate, which is step number 3 in the test of hypothesis.
And I can find the p-value by calculating this 3 value, right?
Okay, how do you calculate this one? You go to the applet, you will find the You find the first box, second box. The first box is called the new, second box is called the X, third box is it has greater than, less than, doesn't equal, and then the last one is p-value. So you plug in the new, like let's say T0 is 3 and degree of freedom is 5, and our alternative doesn't equal. So you plug in 3 for the new, you plug in 3 for the X and 5 for the new, which is the degree of freedom, and you choose doesn't equal, it will give you the p-value.
Okay, I got it.
Okay. Any other questions? Okay. This one under the fixed effect. What if the effect is random, like Yij equal mu plus tau I plus epsilon ij, and I assume this one is random effect. In this case, I'm not interested in tau 1 equal tau 2 equal tau 3, or mu 1 equal mu 2 equal mu 3. Again, it's at least one is different. I'm interested in testing H0, sigma tau square equals 0. Again, sigma tau square doesn't equal 0. And use the p-value to test which one is more accurate, which one is the data support, H0 or HA. If the p-value less than alpha, reject H0. P-value is greater than alpha, fail to reject H0. So how do I estimate sigma square and sigma tau square? Estimation, not testing. The sigma square hat is MSE, is already estimated from the ANOVA table. But tau, sigma tau square, you can estimate this one by calculating the MS due to treatment minus MS due to error divided by little n. Those are the two formulas for the variance component. This is the random effect. The last thing we covered in chapter 3 is the power analysis. The power analysis is used to determine the sample size that achieves some power, some significance level, some size effect, and the last one is power, significance level, size effect, and I forgot one more, the last one. The key, the number of treatments. So we need to find the sample size or the number of replicates or the number of experimental units assigned to each treatment, given some power, given some significance level, given some size effect, given the number of treatments we have. There is a function in R that we covered that once you give the power, the significance level, the size effect, the number of treatments, it gives you the sample size should be used, that should be used. If the sample size is 5.2, you approximate it to be 6. You always round it up. This is chapter 3. Done. Any questions? Any questions? Okay, if you have no questions, so see you on the exam.
Professor, would you please upload this video on Canvas?
Yeah, I will do it.
Thank you.
You're welcome.
Can you upload the notes to the Canvas?
The notes will be already on the video, but if I were able to save them, I will upload them. Let
Okay.
me try.
And
not
Professor,
using these.
Thank
Okay,
you.
go ahead.
the office hours is tomorrow at 2.
We have office hours tomorrow, but I don't remember the time. It's already posted on our Canvas page,
Yeah.
but we
Yeah.
have office hours tomorrow.
Thank you so much.
You're welcome. Okay, guys, have a good evening. See you on office hours or see you on the exam day.
Thank you.
Have a great day.
Thank you.
Thank you.
Thank you.